Okay, dear students, now let's again go to another question, and it is going to be the 10th question. So again, using the principle of mathematical induction, we are going to now see how this will be a true statement, okay? It says, show that x to the power of n plus y to the power of n is divisible by x plus y for odd natural number n greater than or equal to 1. Basically, beloved ones, this is always true. For instance, if you substitute a 3 in place of n, x cubed plus y cubed is divisible by x plus y. You see? How can you assure this? X plus y, make x plus y equal 0, and x is going to be minus y. So if you substitute minus y in place of x and have a power of, you see, odd numbers, you do have minus y to the power of n, and the sum with y to the power of n makes 0. So using this approach, we can just verify that x to the power of odd plus y to the power of odd is divisible by what? X plus y. So again, what we need to do is we need to apply a principle of mathematical induction in order to prove this one. So as usual, 3 steps are going to be involved. Those 3 steps must be remembered here. So as usual, again here, we are going to assign p of a certain variable. So since everything is written in terms of n, again we need to assign this to be p of n. So the solution runs like this. Have p of n to be x to the power of n plus y to the power of n is divisible by x plus y for odd what? Natural number n greater than or equal to 1. So let's now check for the first step. So the first step here is, see, to check for the first given natural number. The first given natural number here is 1, so we directly substitute 1 in place of n. And then we have here p of 1 to be x to the power of 1 plus y to the power of 1. Look here, x to the power of 1 plus y to the power of 1 simply means x plus y. Do you think that x plus y is divisible by x plus y? Yes, because x plus y is 1 times x plus y. So this shows you that this is a true statement. So the first step is satisfied. If again this fails, as I frequently told you, see, this would have, we would never go to other steps. Rather, we stop here saying that this statement is false. But due to the fact that this is true, you see, we need to go to what? The second step. So coming to the step 2, what we have here is, you see, assumption, guys, assumption. We have to assume that this is true for n is equal to k, or assume this statement is true up to a certain natural number k. Look, let you take 101 here, student. X to the power of 101 plus y to the power of 101 is divisible by x plus y. True. True. What if I take 1001? It also again holds true. So whatever natural number I may place in place of n, this always holds true. But is that the way that I need to prove? No. It can't be, because substituting, you see, natural numbers in place of n, you see, is not a means of, you see, showing that this is what? Always true. You have to create a mechanism where you can show this, you see, for the infinite natural numbers, okay? And to do that, you see, the principle of mathematical induction is very important. So what you need to do is you have to assume that this always works, or assume that this holds true up to a certain natural number, what? K. That k has to be odd natural number, because at the beginning it is assumed to be odd natural number, so assume it holds true for, you see, a certain odd natural number k. So if this is so, then you have to assume, you have to accept that p of k is x to the power of k plus y to the power of k is divisible by x plus y for odd natural number k. So you have accepted now this is true up to a certain, you see, odd natural number k. If that is so, if a number is divisible by x plus y, it is true that the number can be written as a certain integral and a certain natural multiple of x plus y. Look here, x to the power of k plus y to the power of k can be written as x plus y times m. For some m, what? Natural number m. You see, natural number. Let me just try to explain this in the following approach. If you are saying that, for instance, 6 is divisible by 3, you see, this means 6 is equal to 3 times 2. If you are saying that 125 is divisible by 5, it's clear that 125 is 5 times some other natural number, which actually is 25. You see, so if a number is divisible by x plus y, then clearly we can say that the number, the expression, as you see, is a certain natural multiple of what? This x plus y. So by assumption, if you accept that this p of k is true, then this follows. X the power of k plus y, the power of k is a multiple of what? X plus y. It's a multiple of x plus y, or natural multiple of x plus y. Beloved ones, I'm going to apply this later. Have this please. Now follows step 3. What we need to do in step 3 is, if this works up to a certain natural number k, are you able to show that this again works for the next natural number k plus 1? You see, that is the one we need to show. Since this is not a fixed natural number k, if you are able to show that the statement is again true for the next or the upcoming, you see, odd natural number, then we can directly say that this holds true for every odd natural number. So we need to show that p of n is true for the next odd natural number. Now there is one thing that I would like to explain here for you guys. Look, if you assume that k is your what? Odd natural number, the next odd natural number can't be k plus 1. And instead k plus 2 is going to come. And remember, 3 is an odd natural number. So the next odd natural number is obtained adding 2 on 3, and that is 5, right? But what will happen if I add 1 on 3? It will be 4. In this case, it can't be what? Natural number, okay? That's why I'm adding 2 here, okay? That's why I'm adding 2 here. So adding 2 on a certain natural number makes you have another natural number. So we need to consider k plus 2 here. This is somehow special compared to those examples we saw before. So we need to show that this p of n is true for n equals k plus 2, where k is an odd natural number, right? So if p of n is asserted in this form, what we need to do is put k plus 2 in place of what? N here. So we do have p of k plus 2, and this is x the power of k plus 2. See, students, x the power of k plus 2, a matter of plugging k plus 2 in place of n, as you see, k plus 2, and again here k plus 2, you see, is divisible by x plus y. So look guys, if we are able to show that this is true, we are done. You see, we can say that this statement is true for any odd natural number. But the question is, how can we show that this is true? To do this, what we need to do is we have to create a mechanism somewhere over here where we can apply the assumption here, okay? So you have to do a means of having x the power of k plus y, the power of k over here, so that in place of that we can use x plus y, you see, times m. You see, this is a technique that we are, you see, the technique we frequently are applying in the case of principle of mathematical induction. So we have to do that, okay? We need to have a means of, you see, a means of this expression, x the power of k plus y is the power of k somewhere over here, obtained from this one. So let's start from this directly. X the power of k plus y is the power of k plus 2. Guys, this is equivalent to this one. Look, x the power of k plus 2 at the beginning is x the power of k times x the power of 2. Look, the bases are the same, so we can add the exponents, so we can have this one as you see. Then you see y is the power of k plus 2 is the same. Y is the power of k times y is the power of 2. Here I wrote, look, here it is. But in between, you see, in the middle, in between, I just have written these two terms, but these two terms one can cancel the other. Look, x the power of ky squared minus x the power of ky squared. One can cancel the other. I just have written this intentionally because I need to make a means of having this one. You see, students? So, you see, I have to create, you see, a mechanism of having this. In order to have that one, I have introduced these two terms. You see, these two terms. Having these two terms never affect the equality sign here, because these two can cancel and we can have this expression directly. So look here, x the power of k is here, x the power of k is here. So I can take x the power of k as a common out. What about here? With the power of, y squared is here again y squared is here, so I can take y squared as a common out. So when I do that, I do have this expression. Look, x the power of k is already taken, then x squared minus y squared is going to come, because x the power of k is already taken as you see, so this is left over. Then come here again. Look, y squared is taken out, so x the power of k plus y the power of k follows. Look guys here, x squared minus y squared, as you remember from your, you see, elementary mathematics class, x squared minus y squared can be written as x minus y times x plus y. Is that not, student? I hope you understood. X squared minus y squared can be written as x minus y times x plus y. Our intention is to have this x plus y, look, this x plus y here and there, because later I can take x plus y as a common out and obtain the x plus y to be a factor of this one. Look, so my intention is to have this x plus y in both these two what terms. So this can be, you see, this can be written as x minus y times x plus y. How about here? Look, it has been assumed that x the power of k plus y, the power of k is a multiple of what, student? X plus y. You see this assumption I am making, you see, this condition, because I can use this one. Look, x the power of k plus y, the power of k, as you see, is, you see, a multiple of x plus y, because it has been said that it's divisible by x plus y. So in place of x the power of k plus y, the power of k, I can use x plus y times m directly, okay? So from this, what follows is this one. X squared minus y squared is, see, a product of these two binomials, as I tried to explain earlier, and x power of k plus y, the power of k is x plus y in times m from the assumption. So now, look, the above expression is going to be equivalent to this one. You see, students, in place of x squared minus y squared, I directly use x minus x plus y, and again here y squared is taken as it is, x the power of k plus y, the power of k is kept to be x plus y times m because of the assumption here I have. Now look, x plus y has appeared twice, you see, so am I able to take this x plus y as a common out? Why not? Possible. So this is going to be x plus y into x the power of k, x minus y plus my squared. Look what I did. I just took x plus y as a common out. So this is going to what? Left over. So have that as it is, x the power of k into x minus y. Then when you check this out, m times y squared can come. You see, students? Now x plus y is obtained to be a multiplier. You see, students? X plus y is a multiplier of what? The x plus y is obtained to be a multiplier, so x plus y is a factor of this expression. You see, students? Factor of this expression, or we can say that this is divisible by x plus y, as you see, because what you are having here is going to be a certain natural number, so x plus y is a factor of this one, or this is divisible by x plus y. So what is assured? P of k plus 2 is assured. Make this to be please 2. So P of k plus 2 is assured. Make this to be number 2. So if P of k plus 2 is assured, step 3 is assured. And if step 3 is assured by the principle of mathematical induction, the statement that says x the power of n plus y the power of n is divisible by x plus y for any odd natural number n greater than or equal to 1 is a true statement because of the concept, or because of, you see, the principle of mathematical induction.